In this video, we'll talk about the first part of the Fundamental Theorem of Calculus. The Fundamental Theorem of Calculus basically, in my opinion, is sort of the capstone of a Calculus 1 course. It serves two main purposes. The first is to formalize the fact that integration and differentiation are inverse operations. And the second is the connection between indefinite integrals, which we talked about a long time ago with antiderivatives, and definite integrals. Those motivations why is all true, but that's not the part you have to know. You have to know really how to apply these theorems to solve different types of problems. Here's part one. Let f be an integral function on the interval from a to b. Define a of x, a new function, by the definite integral from little a up to x of t dt. This here is finding the area under the curve between a and x. We've got this area function that defines the area under the curve between a and x. Then what happens? Well, then if I differentiate a, I get my function f back. So if I take the definite integral, find the area under the curve between x and a, I differentiate that function in x, I'm going to get my function f back, the function that was under the integral in the first place. What does this really tell us? Well, this tells us that definite integrals, so areas under curves, are also in some sense an inverse operation differentiation. We had indefinite integrals that way before. That's how we defined them. They were the opposite differentiation got you the indefinite integral. But now we see here that if I take the definite integral and differentiate that function, that also gives me my function back at the start, so it's also an inverse operation to taking the derivative. It's even more surprising if we didn't use the same notation for these two things, but, so be it. So why is this true? Well, how do we find the derivative of a? Well, a is a weird function, so the only thing we really have is to do it by definition. I know it's been a while, but we're going to do it that way anyway. So a prime at x should be the limit as h goes to 0, a of x plus h minus a of x all over h. Then to work this out, the question really becomes, what is this? Well, this right here is the area from a up to x plus h, subtracting the area from a up to x. You can also think about this using our adjacent intervals formula for definite integrals. This ends up being the area under the curve between x and x plus h. It looks something like this. Right over here is what we're actually finding. A of x plus h minus a of x gives me this area here. Now the point here is I can approximate that area with a rectangle. Either rectangle will work here, but the point is this rectangle here gives a good approximation to that area as long as h is small. And since I'm limiting h to 0, this is a really good approximation. So this area here is a of x plus h minus a of x. What's the area over here? Well, this rectangle here, this bottom one here, has area h, because that's the width of that interval, times f of x. So what I can say then is I can approximate this by the limit as h goes to 0 of that area, h times f of x over h. The h's now cancel, and this ends up equaling f of x. And by some other argument, you can make that as h goes to 0, this error that I'm making goes to 0 as well, so I actually do get f of x here for my answer. So I get that a prime is f of x. And that's sort of why this theorem here works. Notation-wise, you'll notice that when I defined my function a of x, I had the integral from a up to x of f of t dt. So this letter in here was not the same as the x that's up here and that's out here. It's important to keep those straight. You don't want to use the same letter because then you'll sort of get confused with what's going where and how this all things work out. It's important to make sure you keep the letters separate here so you know what's going on. The x only is the thing at the top of the integral. It's nothing inside the actual integrand itself, it's just on top. And so you want to make sure you use a different variable when writing these out. So, what does this give us? Well, for example, if I want to take the derivative of the integral from 3 up to x of sine of t dt, my formula says that's just going to be f, the inside function where I plug in x. This should be just sine of x. Another example, derivative of integral from -1 up to x of e to the t squared dt. Well, that's just going to be e to the x squared. I just take the function inside, that's e to the t squared, I plug in the x for the t, and that's what I get. What if it's not so simple? Well, in that case, you have to do a little manipulation to see what you can get before you actually solve this out. For this one, it's not too bad, because b of x is the integral from x up to 5 of t squared dt. I can switch the order of integration here, and I then get negative integral from 5 up to x of t squared dt. This then means that b prime of x is just going to be negative x squared, because this minus sign here is going to carry down, and this part will just be x squared. So if the x is on the bottom, you get a minus sign. Now what else can we do with this? What if it's not just an x? Here I have a of x is the integral from 0 to x squared of sine of t dt. I can do the same thing, but now I want to think about that x squared as a single unit and see what I get. So if I let u be x squared, what do I have? Well, I have that a of x is the integral from 0 up to u of x of sine of t dt, which means I can write this as an a of u of x, with the function a of u being integral from 0 to u of sine of t dt, which I can do things with, and then u of x being x squared. So I can differentiate this using the chain rule. So I'm going to get a prime of x should be a prime plugging in u of x, and then times u prime of x. A prime for u is just sine of u, because that's how I differentiate this function up here. The derivative of that is just sine of u. So if I do that, I will get that this is sine of u times u prime of x. U is x squared, u prime is 2x, so I get 2x sine of x squared for this derivative here. And so that's the idea of the first part of the Fundamental Theorem of Calculus. Finally, we can differentiate integral functions and get the original function back that we started with. And there's also some examples of certain numbers you can now take of these functions to get certain answers from them.